In 2019, a radio telescope in Australia detected something that made even the most skeptical astronomers pause. A signal at 982 megahertz appeared to be coming from Proxima Centauri, the closest star to our sun, just over 4 light-years away. The signal was narrow, stable, and showed a slow drift in frequency that matched what you would expect if the source was moving relative to Earth. It persisted across multiple observations spanning about 30 hours. Scientists labeled it BLC-1, Breakthrough Listen Candidate 1, and for months it was treated as a genuine technosignature, the kind of signal that could only come from technology. The problem was not that scientists wanted it to be aliens. The problem was that they desperately hoped it was not. Because if it was real, humanity would face the implications of intelligent life existing within reach of our fastest spacecraft, and we would have no idea how to respond or what it meant for our place in the cosmos. Follow-up analysis in 2021 traced the signal back to Earth, likely from subtle instrumental interference or mundane radio pollution that mimicked an extraterrestrial source. Relief washed over the SETI community, followed quickly by unease. Our detection systems are now sensitive enough to find signals that look engineered, that pass every initial filter, and that still turn out to be ghosts of our own technology. The uncomfortable truth is that this could happen again at any moment, and next time, the source might not be so easy to explain away. Fast radio bursts are among the most energetic phenomena in the universe. In a single millisecond, one of these bursts can release as much energy as the sun emits in days, and they come from galaxies billions of light-years away. For years, astronomers assumed they were random, one-off cataclysmic events. Then in 2020, researchers discovered FRB 180916, a repeating burst source that did something no one expected. It operated on a schedule. For roughly 4 to 5 days, the source erupts with bursts at a rate of about 1 per hour. Then it falls completely silent for about 12 days. Then the cycle repeats with precision, locked to a 16.35-day period. This is not the behavior of a random explosion. This is the behavior of something mechanical, something with structure. The leading idea is that the source is a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's, possibly in a tight orbit with another star. As it swings through its orbit, it might only be able to produce bursts when it points toward us, creating the on-off window. But no model fully explains both the extreme energies and the clockwork timing. If fast radio bursts are just magnetars, they are terrifying enough. Magnetars are dead stars compressed to nuclear densities with magnetic fields so intense they warp space itself. But if they are something else, something we have not yet identified, then the catalog of possible cosmic catastrophes near us becomes richer and stranger than we care to admit. Scientists quietly hope the magnetar explanation holds. The alternative is that we are seeing signals from objects or processes that do not yet exist in our physics. Around 2014, multiple independent teams scanning X-ray data from galaxy clusters noticed something odd. There was an unexplained emission line at 3.5 kiloelectron volts. An energy level that did not match any known atomic transition. It appeared in clusters like Perseus and in nearby galaxies like Andromeda. The signal was faint but consistent across different instruments and different targets. One interpretation immediately caught fire in the physics community. If the line came from the decay of sterile neutrinos, a hypothetical type of dark matter, it would be the first time dark matter had revealed itself through anything other than gravity. Dark matter makes up about 85% of the matter in the universe, but it has never been directly detected. It does not emit light, does not absorb light, and only interacts with ordinary matter through gravity. A signal like the 3.5 kiloelectron volt line would be a breakthrough, the first non-gravitational fingerprint of the substance that shapes galaxies and holds the universe together. Researchers spent years trying to confirm it. Then, in 2024 and 2025, deeper reanalyses using better models and more data showed that the signal was likely an artifact. Subtle errors in how the original teams reconstructed spectra, combined with instrumental systematics, had created a ghost line that was never really there. The strange part is that many cosmologists quietly hoped the line was real. Without it, dark matter remains a theory that works perfectly in simulations, but refuses to show up in any detector on Earth or in space. It explains the rotation curves of galaxies, the structure of the cosmic web, and the fluctuations in the cosmic microwave background. But it tells us almost nothing about what dark matter actually is. The vanishing of the 3.5 kiloelectron volt line left physicists back where they started, with a universe made mostly of something invisible that refuses to reveal itself. In 2020, astronomers announced the detection of phosphine in the atmosphere of Venus, a discovery that set off immediate controversy. Phosphine is a molecule that on Earth is produced by life, by industrial processes, or by extreme chemical reactions in environments like deep sea vents. Venus, by contrast, is a hellscape. Its surface temperature is hot enough to melt lead, its atmosphere is made mostly of carbon dioxide with clouds of sulfuric acid, and its air pressure at the surface is 90 times that of Earth. Nothing we know of should be making phosphine there. Other teams quickly challenged the finding, arguing that the signal might be contaminated by sulfur dioxide or might be an instrumental artifact. Some reanalyses failed to replicate the detection, but in 2024, the original team came back with new observations from upgraded instruments on the James Clerk Maxwell Telescope and the ALMA array in Chile. They reported detecting phosphine again, and they found additional support in archived data from NASA's Pioneer Venus probe from 1978, which hinted at phosphine concentrations in the parts per million range. The implication is far more unsettling. Venus might have atmospheric chemistry that we fundamentally do not understand. The upper clouds of Venus, at altitudes where temperatures are more moderate, have long been speculated as a possible niche for extremophile microbes. But even Earth's toughest known organisms could not survive in concentrated sulfuric acid. If phosphine is really there, and if it is not biological, then Venus is producing it through some chemical pathway that does not exist in our models. Scientists would prefer the detection to be wrong, because the alternative is admitting that a planet we have studied for decades still harbors processes that make no sense. The standard model of cosmology assumes that every galaxy is embedded in a massive halo of dark matter, often 10 times more massive than all the visible stars and gas combined. This dark halo is what holds the galaxy together, prevents it from flying apart as it rotates, and provides the gravitational scaffolding for stars to form. Then astronomers found NGC 1052-DF2, an ultra-diffuse galaxy about 65 million light-years away that appeared to contain almost no dark matter at all. Its stars moved at speeds consistent with the mass of the stars themselves, with no need for an invisible halo. At first, some researchers suspected a measurement error. Maybe the galaxy was closer than estimated, which would change the inferred mass. But follow-up observations confirmed the distance, and then a second galaxy in the same region, DF4, showed similarly low dark matter content. The current leading explanation is that these galaxies were formed in a violent collision between dwarf galaxies, a cosmic bullet that stripped away the dark matter and left behind the stars. Recent work has even searched for a trail of dark matter along the axis connecting DF2 and DF4, finding hints that such a collision might have occurred. Researchers hope these galaxies are rare flukes of cosmic violence that do not challenge the broader framework. But if galaxies can routinely shed their dark matter or form without it, then the neat picture of galaxy formation, where gas cools inside static dark matter wells and collapses into stars, is incomplete. It would mean dark matter halos are more dynamic, more fragile, and more poorly understood than simulations suggest. And it would open the door to the possibility that some galaxies never had dark matter to begin with, which would shatter our understanding of how structure forms in the universe. In 2013, astronomers cataloged the Huge Large Quasar Group, a collection of more than 70 quasars that form a single structure nearly 4 billion light-years across. To put that in perspective, the observable universe is about 93 billion light-years in diameter, and the huge LQG spans a significant part of the sky at its redshift. Structures this large violate the cosmological principle, which assumes the universe appears statistically the same in all directions when averaged over large scales. Cosmology suggests structures should not exceed about 1.2 billion light-years, based on the universe's homogeneity on large scales. The huge LQG is over 3 times that size. Later analyses proposed that grouping algorithms and selection effects could make random quasar associations appear as coherent structures, suggesting the apparent violation might be a statistical fluke. However, the effort needed to defend the principle highlights its fragility. Patterns and alignments in galaxy and quasar distributions challenge the uniform universe assumption. If the cosmological principle fails on large scales, it threatens the foundation of modern cosmology. Our equations for universe expansion, structure formation, and dark energy evolution rely on space being, on average, uniform. If it's not, with preferred directions or regions of differing properties, models are incomplete, and the universe may be more complex than previously thought. Scientists hope the huge LQG is a mirage. Otherwise, it indicates structure on scales we never expected to see. The Hubble constant is a number that describes how fast the universe is expanding now. It should be easy to measure in cosmology, determine galaxy distances, measure their recessional speeds, and calculate the rate. Yet over the last decade, different methods have produced vastly different results, with the gap widening despite better data. Cosmic microwave background measurements, the afterglow of the Big Bang, give a value around 67 kilometers per second per megaparsec. Local distance ladder methods, using Cepheid variables and supernovae, suggest about 73. This difference, while seemingly small, constitutes a crisis in cosmology. Recent observations from the James Webb Space Telescope confirm that the discrepancy isn't due to crowding errors or instrumental biases in earlier Hubble data. Independent techniques, such as gravitational lensing time delays and other distance measures, also support the higher value. If the tension is real, it suggests two possibilities. Either there's a systematic error every method misses, or the standard cosmological model is incomplete. The latter worries cosmologists most. If the Hubble constant varies based on measurement method, it likely indicates new physics. Perhaps dark energy behaved differently in the early universe. Additional neutrino species or altered gravity on cosmic scales could also be factors. Such changes would drastically reshape our understanding of galaxy formation, dark matter clustering, and the universe's fate. Many hope the tension is genuine, as it might reveal fundamental new physics since dark energy's discovery. However, they also fear that resolving it could fragment the standard model into patchwork fixes that lack coherence. The cosmic microwave background is the oldest light in the universe, a snapshot of the cosmos at 380,000 years old. It is also one of the most uniform measurements, with temperature variations across the sky about 1 part in 100,000. However, analysis of the largest scale patterns reveals strange features. The quadrupole and octupole components, representing the biggest temperature fluctuations, are oddly aligned, contradicting the expectation of a statistically isotropic universe. This alignment, called the axis of evil, points in a specific sky direction. Follow-up studies have examined whether this alignment appears in CMB polarization data, aiming to confirm it as a genuine primordial feature rather than noise or foreground effects. The results are suggestive but inconclusive. The anomalies may persist or disappear under better models. There is also a notably cold and large spot in the CMB, possibly linked to a supervoid, an enormous underdense region. Though this doesn't fully explain its extreme cold. If these anomalies are real, they imply a preferred direction on large scales, challenging the assumption that space is isotropic. Some models suggest anisotropic inflation, where early expansion was faster in certain directions, or cosmic defects like strings or domain walls that could imprint patterns on the CMB. None of these are widely accepted. The unsettling possibility remains that the Copernican principle, the idea that we occupy a typical region, might be weakened. Perhaps we live in a large-scale feature that biases our observations. Scientists hope better data will reconcile these patterns. Otherwise, it suggests a universe with an unexplained directional memory. The Sun rotates with its axis tilted about 6 degrees relative to the planetary plane. Though small, this is unusual because standard solar system formation models suggest that the Sun and planets, formed from a single rotating disk of gas and dust, should share the same angular momentum axis. The Sun's tilt remains unexplained. One possible explanation is a distant, unseen planet called Planet 9, which would be 5 to 10 times Earth's mass, orbiting beyond Neptune on an elongated, inclined orbit. Over billions of years, its gravity could tilt the outer planet's orbits and the Sun's axis, and explain clustering among trans-Neptunian objects. Models show a planet with the right orbit could account for the Sun's tilt and Uranus spinning on its side. Decades of surveys have not found Planet 9, and some argue the observed orbital clustering is due to observational bias or collective gravity of small objects, not a single large planet. Yet the hypothesis persists because it explains multiple anomalies with one cause. If real, the solar system would be more complex, shaped by an unseen giant that could destabilize the outer regions, send comets inward, and impact Earth's history. Our familiar neighborhood would remain fundamentally unsettled. These unexplained phenomena highlight where data challenges models, suggesting the universe may be more mysterious than our elegant equations indicate. Historically, anomalies have often marked the next scientific frontier. If these theories unsettled you, watch Scary Places in the Universe next. It explores real cosmic environments where physics breaks down completely and makes these ideas feel far less hypothetical. Thanks for watching.